All right, so to really get this, let's travel back in time. The year is 1925. The world of physics is absolutely buzzing with the new, frankly bizarre rules of quantum mechanics. But there was this huge problem, a loose thread that nobody, and I mean nobody, could figure out.
Okay, so here's what they had. Physicists knew that electrons inside an atom were described by three quantum numbers. You can kind of think of them like a quantum address or coordinates. But, and this is a big but, when they looked at the light coming from atoms, they saw this weird splitting pattern called the anomalous Zeeman effect that just didn't fit the theory. So to try and fix this, the brilliant Wolfgang Pauli suggested, hey, maybe there's a fourth number. The problem? Nobody, not even Pauli himself, had any clue what this number physically represented. It was like a ghost in the math. What did it actually mean?
Now, you'd think the answer would come from one of the established giants of physics, right? Nope. It came from two young grad students at Leiden University, George Uhlenbeck and Samuel Goudsmit. They were just buried in all this confusing data, and they came up with an idea that was, well, it was daringly simple.
Uhlenbeck had this incredible aha moment. He figured, look, if every other quantum number describes the way the electron can move, a degree of freedom, then this fourth number must be a new degree of freedom. And his conclusion was as simple as it was totally radical. The electron itself has to be spinning.
And this is the core of their idea, what they called intrinsic spin. The electron isn't just some point floating around a nucleus. It has its own built-in angular momentum, just like a tiny spinning top. And here's the kicker. Because it's a charged particle, that spin creates its own little magnetic field. And just like that, the mysterious fourth quantum number suddenly had a real physical meaning.
But, of course, it's never that easy, is it? As soon as they came up with this brilliant idea, it just smacked right into a brick wall. See, the most respected physicists at the time immediately pointed out a huge flaw. A spinning charged particle seemed to break the known laws of physics. So the idea was in serious trouble before it even got off the ground. In fact, the pushback was so strong, coming from the absolute legend Hendrik Lorentz, that Uhlenbeck and Goudsmit completely lost their confidence. They were totally convinced they'd made a huge, embarrassing mistake. They literally ran to their mentor, Paul Ehrenfest, and begged him to stop their paper from being published.
And this is where we get one of my favorite lines in the entire history of science. Ehrenfest basically told them, sorry boys, it's too late. I already sent the paper in. And then he said this incredible thing. He was encouraging them to take a risk. He saw the genius hidden inside their stupidity, and he shoved it out into the world, even when they wanted to hide it.
So they dodged one bullet. But even after the paper was out there, the idea faced its biggest challenge yet. This wasn't just some philosophical debate anymore. This was a cold, hard math problem, a flaw that seemed to prove the whole theory was just dead wrong. The heavyweights of physics started weighing in. And, well, the news was not good. Wolfgang Pauli, the guy who came up with the fourth number to begin with, he just flat out rejected it. And Werner Heisenberg, another founding father of quantum mechanics, sent them a letter that was basically a polite way of saying, you messed up. He congratulated them on their brave note, but then he dropped the bomb. How did you get rid of the factor of 2?
And this was the killer, the factor of 2. When you actually did the math with their spinning electron model, the energy level splitting it predicted was exactly twice as large as what scientists were actually measuring in their labs. Their beautiful, elegant idea was quantitatively wrong, off by a precise and pretty damning factor of 2.
So, our two young physicists are completely stuck. Their theory looks dead in the water. But then, in an amazing stroke of luck, who happens to be visiting Leiden at the time? None other than Albert Einstein. And he was the one who pointed them toward the solution. So Einstein tells them, hey, you're looking at this all wrong. You need to think relativistically. He tells them to change their perspective. Instead of standing outside the atom looking in, what if you were riding on the electron? Well, from the electron's point of view, it's the positively charged nucleus that's whipping around it. Now, that moving charge creates a huge magnetic field. But, and here's the absolutely genius part, because the electron is on a curved path, a special relativistic effect called Thomas precession kicks in, and this weird little quirk of space-time just happens to cut that magnetic interaction exactly in half. It introduces a factor of 1/2 that perfectly cancels out that extra factor of 2.
And boom, just like that, the biggest objection vanished. The math suddenly lined up perfectly with the experiments. The stupid idea wasn't just a nice little story anymore. It was actually quantitatively correct. Electron spin was real. After that, everything happened fast. It was like a domino effect. By December of 1925, even the super skeptical Pauli was on board. And with encouragement from other giants like Niels Bohr, Uhlenbeck and Goudsmit published their full, detailed paper. And that was the one that truly sealed the deal, cementing electron spin as a fundamental property of our universe.
So it all comes back to that first question, doesn't it? The story of electron spin is just this amazing reminder that progress in science often demands the courage to put forward an idea that seems a little bit foolish, maybe even a little bit crazy. And just as important, it requires mentors who are willing to let you afford a stupidity. It really leaves you wondering, what's the next big stupid idea out there, just waiting for someone brave enough to see it through?